Previously, in section 20.1 and 20.2, we discussed redox reactions. And remember, the word redox is a combination of reduction and oxidation, where reduction is the gaining of electrons and oxidation is the losing of electrons. And so essentially we have an electron transfer between two materials. In this image, we see a spontaneous redox reaction occurring between a piece of zinc metal when it's placed in a solution of copper. And the problem is, yes, electrons are transferred from one material to the other, but there's really no way for a scientist to harness that energy if they're in direct contact like that. So this section, 20.3, will discuss voltaic cells, really batteries, and how they produce their energy. And to start with, we're just going to watch a quick TED Talk on batteries that gives a nice overview of how they work.
You probably know the feeling. Your phone utters its final plaintive bleep and cuts out in the middle of your call. In that moment, you may feel more like throwing your battery across the room than singing its praises. But batteries are a triumph of science. They allow smartphones and other technologies to exist without anchoring us to an infernal tangle of power cables. Yet even the best batteries will diminish daily, slowly losing capacity until they finally die. So why does this happen? And how do our batteries even store so much charge in the first place? It all started in the 1780s with two Italian scientists, Luigi Galvani and Alessandro Volta, and a frog. Legend has it that as Galvani was studying a frog's leg, he brushed a metal instrument up against one of its nerves, making the leg muscles jerk. Galvani called this animal electricity, believing that a type of electricity was stored in the very stuff of life. But Volta disagreed, arguing that it was the metal itself that made the leg twitch. The debate was eventually settled with Volta's groundbreaking experiment. He tested his idea with a stack of alternating layers of zinc and copper, separated by paper or cloth soaked in a saltwater solution. What happened in Volta's cell is something chemists now call oxidation and reduction. The zinc oxidizes, which means it loses electrons, which are in turn gained by the ions in the water in a process called reduction, producing hydrogen gas. Volta would have been shocked to learn that last bit. He thought the reaction was happening in the copper, rather than the solution. Nonetheless, we honor Volta's discovery today by naming our standard unit of electric potential the volt. This oxidation-reduction cycle creates a flow of electrons between two substances, and if you hook a light bulb or vacuum cleaner up between the two, you'll give it power. Since the 1700s, scientists have improved on Volta's design. They've replaced the chemical solution with dry cells filled with chemical paste, but the principle is the same. A metal oxidizes, sending electrons to do some work before they are regained by a substance being reduced. But any battery has a finite supply of metal, and once most of it has oxidized, the battery dies. So rechargeable batteries give us a temporary solution to this problem by making the oxidation-reduction process reversible. Electrons can flow back in the opposite direction with the application of electricity. Plugging in a charger draws the electricity from a wall outlet that drives the reaction to regenerate the metal, making more electrons available for oxidation the next time you need them. But even rechargeable batteries don't last forever. Over time, the repetition of this process causes imperfections and irregularities in the metal's surface that prevent it from oxidizing properly. The electrons are no longer available to flow through a circuit, and the battery dies. Some everyday rechargeable batteries will die after only hundreds of discharge-recharge cycles, while newer advanced batteries can survive and function for thousands. Batteries of the future may be light, thin sheets that operate on the principles of quantum physics and last for hundreds of thousands of charge cycles. But until scientists find a way to take advantage of motion to recharge your cell battery, like cars do, or fit solar panels somewhere on your device, plugging your charger into the wall rather than expending one battery to charge another is your best bet to forestall that fatal bleep.
So a voltaic cell takes the energy released from a spontaneous, forcing the energy released from a spontaneous redox reaction to flow through an external device. So rather than having the two materials like in the first picture, the piece of zinc metal and the copper solution, rather than having them in direct contact, we force those electrons to flow through an external circuit or device or wire, which could then creates a flow of electrons, which, as you know, is electricity. The nice thing about that is since we're forcing them through that external device, it can then be used to do useful work. Here's an example of a voltaic cell, and there are several features to kind of make observations about and make sure you are seeing when you look at this kind of complicated diagram. We do see that we have two compartments, two electrodes, if you will, called the anode and the cathode, and we're going to talk about ways to remember those. On the left in this image we have the zinc electrode or zinc anode, and it's a piece of zinc metal, and it's in a solution that contains zinc ions. Now they have chosen to go with zinc nitrate, but really you could pick zinc chloride, some other zinc salt as well. The right-hand compartment, the other electrode, contains copper solid, which we call the copper cathode, and then a solution of copper ions, and that's why it's colored as blue. And so here, again, we have copper nitrate, but again, another copper salt of some sort would have worked as well. The important parts of each of those electrodes are really the solid and the ions in each case. And so notice in each half cell or half part of the battery, you have both a solid and an ion present. Now, one is an oxidation reaction and the other is a reduction reaction, and so together they comprise a redox reaction. We know that oxidation always takes place at the anode and reduction takes place at the cathode, and one of the mnemonic tricks you can use to remember that is red cat, reduction, cathode. Or you can also remember their vowels and consonants. We have an O and an A and an R and a C. There's several ways actually to do it. So you have your two compartments. We know that electrons always flow from the anode to the cathode, and the reason why, if we have an oxidation reaction happening at the anode, the definition of oxidation is losing electrons. So as zinc solid is turned into zinc plus 2, we have these electrons being lost, and then in turn they can flow to the other side, the other electrode, where then copper ions from the solution will actually gain those 2 electrons and turn into copper solid. Now, one of the other features of every voltaic cell is a salt bridge, and it's often a U-shaped tube, like shown here in the picture, that contains some sort of salt. I always use either potassium nitrate or sodium nitrate as I'm prepping my salt bridges, just because the alkali ions are always soluble, and as you know from our solubility rules, nitrate ions are always soluble as well. Now, the direction that ions flow in the salt bridge is always the same. Cations, always move toward the cathode, and anions always move toward the anode. Now, some of you I know are thinking like, ooh, likes repel or something along those lines, and thinking that doesn't really seem to make sense. But you have to consider the half reactions occurring in each cell. And so if you look at the anode compartment, okay, the half reaction occurring there is zinc turning to zinc plus 2 and then 2 electrons. Now remember, the 2 electrons are not staying there. They do flow through the from the anode to the cathode and leave. That would leave a buildup of positive charge of zinc plus 2 ions. And if that positive charge accumulates, really this cell is not going to continue to function. So to keep the charges balanced, we have some anions that come from the salt bridge down into that compartment to neutralize the buildup of those positive zinc ions. In the other compartment, we have copper ions. Now, The other compartment is the cathode, red cat. That's where reduction is happening. And reduction is gaining electrons. So these copper ions are actually leaving and gaining 2 electrons to turn into copper solid, which means you have all the nitrates left behind, which are negative. So the cathode compartment, if you don't do anything with it, would have a buildup of negative charge. And so to balance that out, from the salt bridge, we have sodium ions, or some sort of cations, that migrate toward the cathode to keep that charge balanced. And it's kind of cool. We will be constructing a voltaic cell or battery, and if the moment you take that salt bridge out, the voltmeter that can be used to measure how much voltage your generator it will drop to 0 instantly the moment that salt bridge is removed. And then as soon as you put the salt bridge back into place, then the electrons will flow, and you really are, in a sense, completing the circuit. One other thing to keep in mind as these 2 half reactions are occurring is the mass of each of the electrodes. Now the anode, remember anode oxidation, if you look at this half reaction here, zinc is turning from solid, and it's really losing electrons and then turning into zinc ions. So the mass of this zinc electrode or zinc anode over time, it will become lighter as this battery or voltaic cell functions, because the zinc solid is turning to ions. It's essentially dissolving. The other compartment, the cathode, is the opposite. The cathode always gets heavier or gains mass as the cell operates, because in this half reaction, in this half reaction we have copper ions turning into copper solid, and so really electrons are picked up by those copper ions, and the solid deposits itself onto this piece of copper, and so over time it does get heavier. So that section, oh, and I have one more little trick or visual for you to help you remember things. We mentioned red cat. I was out on Pinterest and found this this image and knew you guys would like it, so thought I would throw that in there. But just another way to remember which half reaction is happening at which compartment or which electrode in your cell. We have red cat, reduction occurs at the cathode, and an ox, anode, is oxidation. So again, just another way to kind of keep those 2 straight. In the next section, 20.4, we're going to discuss something called electromotive force. Now, in the third section 3 that talks about voltaic cells, it talks about the fact that electrons are flowing from the anode to the cathode, and they always flow in that one direction. But it doesn't really explain a reason why that is happening, just that it does happen. And so hopefully this section will shed a little bit of light excuse me, on how that works. When you talk about electromotive force, or EMF as it's sometimes called, it really comes down to a difference in potential energy. And if a good analogy to think about is a waterfall. And if you think about how a waterfall operates, water spontaneously flows only one direction in a waterfall. It always flows from the top of the waterfall down to the bottom. We never see water down in the collection pool that is jumping up and ending up on the top of that waterfall. And so just like water only goes from the top to the bottom in a waterfall, the electrons only spontaneously flow one direction in a battery or in a voltaic cell. We know that electrons will always flow one way in a redox reaction, and that is from the metal with the higher potential energy to the lower potential energy. And we have talked about potential energy in other settings, in other chapters this year, and we said that things are always looking to obtain their lowest energy possible because that is the most stable. And so if you have like a boulder at the top of a hill and it goes over the hill just a little bit, it has very high potential energy due to gravity, and so that boulder would naturally flow down to its lowest part of the hill, therefore lowering its potential energy and getting rid of as much energy as possible. It's very much the same in a battery, in a voltaic cell, where you have the anode that has a higher potential energy, and it is looking to lower its energy, and so electrons spontaneously flow from that anode to the cathode. So electromotive force, or EMF, is the difference in potential energy, or sometimes they just call it potential difference, between the anode and the cathode. And the anode is always higher in potential energy than the cathode. There are many synonyms used in chemistry and in science to refer to this amount of energy difference. And some of the many terms out there, and you should just kind of have a working knowledge of these terms, because you may be reading a textbook problem or an online problem, and they may use some of these different terms. So it's good to be aware of them. EMF, electromotive force, you can also call them cell potential or cell voltage. A lot of times we will just say, what's the voltage of the cell? That's a common way to refer to it. Potential difference, in just kind of a more slang, common way to say it was, you know, like how much juice does your battery have? If you take a look at a AA battery or a AAA battery that maybe you have in your calculator or something, if you look on the side, it says 1.5 volts. And that means that your anode has a potential energy that's 1.5 volts higher than your cathode. And EMF is written as a symbol as E cell. It's measured in volts, and let's cut off here a little bit. 1 volt is equal to 1 joule per coulomb. Let me write that up here. And as we get into electrolysis at the end of this chapter, we'll want to make use of that. Joules is an energy unit, and coulombs is the amount of charge that electrons can acquire, and volts is kind of measure of those two. I found a couple other funny things that I wanted to pass along. Chemistry cat's always a favorite of mine. I was going to tell you a joke about electricity, but it was too revolting. Thought you guys would like that one. I have two others. This one here we have, okay, copper, what's the charge? A salt and battery. Notice the salt container falling down there. I have contacts, you know, just because, you know, batteries have 2 contacts, so you have to connect on a 9-volt battery. And the last one for the day, what is an electrician's favorite flavor of ice cream? Chocolate. Chocolate. Thought you guys would like those. I certainly did. Now, you should have a handout, I believe it's purple, Appendix E, which is a table of standard reduction potentials. And this handout actually is 2-sided, and there's 2 different ways you can use this table. One side has an alphabetical listing of half reactions, and so at the top, let me get mine out for reference here as well. On the top we have like silver, because alphabetically silver, AG is the beginning of the alphabet, and then it goes all the way through zinc. And it's an alphabetical arrangement, which is handy sometimes to just quickly find one that you need to look for to find the voltage for a cell. But on the other side of the document is another way of arranging the cell potentials, and that is by voltage. And so you will see that we have lithium at the top with the largest negative value all the way down to fluorine down at the bottom. And we're going to talk about why that side may be useful for another application. One thing you should know is that anytime you're looking at one of these reduction potentials, if you see a positive number, it's a spontaneous number, a spontaneous process. So anytime you see a positive number, it will happen on its own. And the example I look at is iodine right here. As for one example, iodine's a halogen, and halogens normally have 7 valence electrons. And so it would be a good thing if iodine could get another electron and turn to iodide ion with 8 electrons. And so that's a spontaneous reaction that would tend to happen. On the other hand, if you have a negative sign for your standard reduction potentials, that's a non-spontaneous process. And I look at sodium down here. Sodium normally has 1 valence electron when it's a neutral substance, but in this case it's a sodium ion. It's already lost 1 electron. And so it's happy that way, it's stable that way, it has 8 valence electrons. So if we were to force it to take that electron back and go back to elemental sodium, that's really would not want that to happen. It becomes less stable in that process, and so we see a negative sign indicating that, hey, that process would not happen on its own, because sodium we know is much more stable as an ion rather than sodium solid or sodium metal. So that's a little bit about the signs, but we also can read in a little bit to the magnitude of the number. And the larger the positive value is, the more likely it will happen, or the fact that it will happen more easily. Now earlier I pointed out iodine, that it's a halogen that is more stable when it acquires electrons. But if we look at the top of this list, fluorine, which has a much larger positive potential here for reduction, 2.87 volts compared to 0.54 volts, we know fluorine is extremely electronegative, and so it would attract those electrons, and that'll happen more readily or more easily than iodine acquiring electrons, even though it's favorable for both of them to do so. One thing I also want to mention is that you'll notice that every single reaction on this handout, Appendix E, all of them are reduction potentials. And so when you have a battery, redox, remember that word, those two things have to happen together. You can't have oxidation without reduction, and vice versa. So all of these are written as reduction, and so you will see that in all cases you find electrons on the left side of the reaction. That's because reduction is gaining electrons. So once we start determining voltage, there will be a way that we can account for the fact that yes, you have to have oxidation as well, and we'll get to that in just a few minutes here. One notable value that we should take a look at on this handout, on this Appendix E, is the hydrogen reaction. And if you take a look at, it's on the left-hand column, kind of very second from the bottom, we have hydrogen ions turning to hydrogen gas, and that is referred to as the standard hydrogen electrode, aka the SHE, we just call it for short. And the deal is all other reduction potential values are compared to hydrogen as a reference standard. And so we call hydrogen, or I should say define hydrogen as having a 0 voltage reduction potential. Not that it actually is 0, but we've just selected that one to be 0, and then everything else is compared to that standard hydrogen electrode. And so if it has a positive value, then it's reduced more easily than hydrogen, and if it has a negative value, then it's reduced less easily, or not as easily as hydrogen. So just think of hydrogen as having the 0 volts just as a definition, and then everything else was compared to hydrogen to obtain all those values in your Appendix E handout. So great that you have a table. How do we use it? So this last part of the section, we're going to talk about how to calculate or how to determine standard cell potentials. And the equation is very straightforward. To figure out the voltage of a cell, or the E cell, or EMF, or potential difference, remember it has a lot of different possible terms, you are going to take the reduction potential for the cathode and subtract the reduction potential for the anode. And so because this equation has this negative sign in it, you don't have to do any flipping of signs or anything like that. You just take cathode minus anode. And keep in mind your overall answer will need to be positive if that reaction is actually going to occur. And so your E cell will be positive if you put the correct combination of materials together, and it will actually happen. One way that this is different than some of the other mathematical processes we've worked on it this year is that in this case we will not be multiplying by coefficients. E cell is an intensive property, which means it's independent of amount. And so it doesn't matter if you have, the silver, if you guys look at your purple sheet, the silver reduction potential, silver +1 going to silver solid, has a value of positive 0.799 volts. It doesn't matter if you have 2 moles or 10 moles or 5 moles, you will still use that same 0.799 volts. You do not multiply by coefficients. And then it's an important distinction compared to some of the other things we have worked on. So I want to revisit the battery or voltaic cell that we were taking a look at earlier, the combination of zinc and copper. And you can see on this voltmeter that it's displaying 1.10 volts, and we kind of want to discuss, how did they come up with that number. And so here's our overall balanced equation, and if you take a look at what's happening in this reaction, zinc is going from zinc to +2, as shown right here. It is losing electrons, and so we know that it's oxidized. Copper is gaining electrons and changing from a +2 to 0, and so in this process it's being reduced. Now remember, red cat and ox, and so we can find each of these on our sheet and then use the equation we just discussed, cathode minus anode. And you should find the zinc half electrode on your purple sheet. I believe it's the last one in the bottom right. Zinc and zinc solid, negative 0.763. Now I know some of you are like, oh my gosh, it's the opposite on my sheet, Mrs. Hohenstein. We're starting with zinc solid and ending up with zinc +2, but that's not how it's written on the sheet. And I understand that. You want to find the same half reaction. I realize it's in the opposite direction, and it's supposed to be because this entire Appendix E is all set up as reduction potentials. And we are currently, for zinc, looking at an oxidation reaction. And so that sign will work itself out when we do cathode minus anode. Now for the other half reaction, or the other cell in our battery, we have copper +2 and copper solid. Now be very careful. Copper shows up in a couple places on your Appendix E handout. There's a copper +2 that gains 1 electron to go to copper +1. That's not the one we're talking about. We are talking about the one that involves copper +2 and copper solid. So make sure you're looking at the same one. And I believe on your handout it's 0.337. This just has the different significant figures. So we do have the two half reactions that we're concerned with. And this is the reaction we would make use of, okay, to find the voltage or the E cell for a reaction. We take the reduction potential for the cathode minus the reduction potential for the anode. And notice, they both say reduction. So we're just going to leave the sign the way it is from the handout. That's why this negative sign here is in the middle. So if we take positive 0.34 volts, minus a negative 0.76 volts, we should come up with 1.1 volts, which is what was displayed on the voltmeter on the drawing. Now a couple of other comments about this Appendix E, the way it's set up kind of on the back side. We know that the larger positive value, now I know this graphic is the exact opposite of the way yours is set up. Yours has the biggest negative number on the top and the largest positive number on the bottom. So it's opposite to this graphic from our textbook. And we will talk a little bit more about why it's opposite of this table. But what I want you to notice, and I believe it's already circled on your handout, the material that is reduced the most easily, that means it accepts electrons or steals electrons from something the most readily, would cause that other material to be oxidized. And so the number that has the largest positive reduction potential should be your strongest oxidizing agent, which I believe is already identified on your handout as fluorine. And the opposite is true. If something does not want to accept electrons very well, meaning it's really more easily oxidized than reduced, then it will be your strongest reducing agent. Because remember, a negative number on this handout means it does not happen easily, and so the largest negative value involves lithium ions going to lithium solid. I believe it's negative 3.05 or something like that volts. And that means that lithium ions have very little tendency to accept electrons, which if you look at the other side then, that means lithium solid really will give up its electrons the easiest to something else, causing something else to be reduced. And so keep in mind they are on opposite sides of this table. The strongest oxidizing agent are the ones with the most positive reduction potentials, and the strongest reducing agents or reducers have the most negative. And we will continue to work with those throughout this chapter and kind of gain some experience with that. The reason that the handout you have is set up from most negative value to most positive value is in that form it doubles as an activity series. And when I used to teach AP chemistry, that's always the way this table was set up, so that like lithium, for example, is the most reactive metal out there, so it's at the top of that table, and then as you go through the list, things get less and less reactive, so that's why it's there. Now, one final comment regarding this handout. Keep in mind the battery or voltaic cell we were looking at involved copper and zinc as our two materials. And by taking cathode minus anode, we came up with a value of 1.1 volts for our battery. Really, the greater the difference between those two reduction potentials, the greater the voltage of the cell. And you might say, well, gosh, Mrs. Holstein, then instead of like copper and zinc, which only differ by 1 volt, maybe we should go with the biggest positive and the biggest negative number. And certainly you would get a higher voltage if you did so, but you might have concerns with availability of materials, cost of materials. If they're too reactive, maybe they're hard to keep in a battery without reacting on their own or creating some other side reactions. And when we get to a little bit later in this unit, we have a lab called electrochemical cells where you guys will combine various half reactions to see which battery can create the largest amount of voltage, and we'll be able to revisit this table again. So that's it for sections 3 and 4. Have a great day.